way to remember. A mosquito was heard to complain to the chemist that poisoned her brain. The cause of her sorrow was para-dichloro, diphenyl, trichloroethane, DDT. So, yeah. I thought you might be that. Okay, so last time we talked about enols and enolates, right? And one of the reactivities that you make use of to make DDT is the reactivity on the left, okay, where this was an aldehyde, trichloroacetaldehyde, the nucleophilic addition to that carbonyl. So this is the reactivity that relies on the partial positive charge of the carbonyl carbonate. But there's another reactivity that ketones show, and aldehydes and esters, any carbonyl compound that has at least one alpha proton. Okay, so if you have at least one alpha proton, you can treat this with a strong base, pull that proton off, and form an enolate. The enolate is nucleophilic. And so you have two kinds of reactivity. You have electrophilic reactivity at the alpha carbon, nucleophilic reactivity at the, electrophilic activity at the carbonyl carbon, nucleophilic activity at the alpha carbon. And so this chapter is going to explore how that leads to lots of different kinds of reactions and how it can be used to generate structural complexity. Okay, so where we left off last time was the addition of an electrophile. Your typical electrophile is what? Iodomethane to an enolate. So enolate, I said, is a nucleophile. Iodomethane is an electrophile. We saw that when we talked about what? SN2 reactions. And so this is an SN2 reaction. Nucleophile does a displacement of a leaving group to form this red bond. In this case, it's a very interesting and useful SN2 reaction because it forms a carbon-carbon bond. Okay? And so this is a very common type of reaction that we're going to see again and again, where you take an enolate and alkylate it. So this is an alpha alkylation. Now, a related process exploits the dual activity of carbonyls. In other words, I said that carbonyls are nucleophilic at the alpha carbon through their enolates, but that the carbonyl carbon is electrophilic. So here I use a carbonyl carbon compound, both as the nucleophile and as the electrophile, to form this red bond. This is a reaction that we're going to see down the line. This is called an aldol reaction. Okay, this is an aldol reaction, and it's because if you use the aldehyde, so that's the al part, and the ol is because the product is an alcohol. So all of these reactions that we're going to talk about are ones that get started by forming the enolate. And so now we need to take a look and see how this enolization process takes place. Now, the first thing that you find out is that the enol is present in equilibrium with the ketone. We talked about this a little bit way back when we talked about hydration of alkynes. And so, if you take a typical ketone like cyclohexanone, there is some enol at equilibrium. This process, by the way, is catalyzed by the traces of acid or base that are present in the glassware, on the surface of the glassware, and you end up with a very, very small equilibrium constant. So you have less than 1/10% of this stuff. Okay? So at equilibrium, it's pretty much all here, a tiny little bit of that. However, because this equilibrium is being established all the time, even though we have a small amount of this stuff, it can have a dominant effect on the reactivity. Now, there are ways to amplify the amount of enol, but we'll talk about that in 5. Esters, you'll notice that for esters, you have even less of the enol at equilibrium. So here, there's really a vanishingly small amount of the enol at equilibrium. And so we can get down to 10 to the minus 20, and really what that's telling you is that there's hardly any there at all. I mean, really nothing. That's a very, very small amount of enol. Why is that? Well, you kind of know why, because the carbonyl group here is a lot more stable than that one. And so, given the fact that this is more stable than that, you would expect less spontaneous enolization. Now, so the question that we have is, well, you have these two different forms. By the way, interconversion of these, you remember, I asked you to go back and take a look at that hydration alkyne. Remember how this happens, right? It happens by a series of proton transfer reactions. So it's nothing fancy going on. You add a proton, lose a proton kind of stuff. The question, of course, is how come? Why is this the dominant form at equilibrium? And what this is telling us is that this is a lot more stable than that. There are really a couple of reasons for this. And one is that the keto form, not the enol, is stabilized by resonance. Okay, so we have a resonance structure for the ketone that's stabilized. The enol doesn't have that, and but primarily it's because the CO bond is stronger than the CC bond. Okay, so the carbon, you're taking a carbon-oxygen double bond in the ketone, and you're exchanging it for carbon-carbon double bond in the enol. It turns out that the ketone CO bond is stronger than the CC bond. So so it makes sense that you would have more of the ketone at equilibrium, less the enol. It's more stable than that. Now, there are two exceptions where the enol actually is the major product, or the major component rather, the major component. And the one that you need to remember is phenol. So phenol, if I kind of look at it, this is not how shall I say? It's not exactly accurate because this double bond is not localized here. Remember, this is a partial bond. But if I just pretend that this is phenol and that I don't have resonance in the benzene ring, I just look at that. That's an enol. Am I allowed to do that? Well, actually, you are allowed to do that because it turns out that phenol does react in some cases like an enol and like an enolate when you deprotonate it. But here, the phenol is, of course, the dominant species at equilibrium. You really don't have any of these two keto forms. I mean, I've shown equilibriate here, but this is aromatic. These two are not. And so there really is no equilibrium here. I've shown this equilibrium, but it's all this. None of it is that. And so the enol is aromatic. This is a stable enol. Okay, there's one. Now, that's not the only one. Whenever I have 1,3-dicarbonyl compounds, 1,3-diketones, ketoesters, diesters, what have you, anytime I have a 1,3-dicarbonyl compound, the enol form is usually present in some significant quantity. And the reason is indicated here, pentane dione. If I draw the enol, it turns out that enol is stabilized by the intramolecular hydrogen bond of the enol hydrogen with the engaging the non-bonding electron pair on the carbonyl. And so for things like pentane dione, yeah, this is it's essentially a 9:1 ratio of enol to diketone. So this is very important for 1,3-dicarbonyl compounds because the enol is stabilized by this hydrogen bond. So this is the exception to the rule. And I've shown one enol, but of course the other ketone can participate. And so I can show this as a series of resonance structures. And it shows the same kind of resonance stabilization as what? As an alpha-beta unsaturated ketone. And so the enol is an alpha-beta unsaturated ketone, and so yes, it has exactly the same resonance structures that you would expect for an alpha-beta unsaturated ketone. Okay, so these are two examples of compounds where the unexpected takes place, where the enol is present in larger amount than the keto form at equilibrium, for the two reasons that I said. In one case, because of aromatic stabilization. In this case, because of stabilization through that hydrogen bonding. So now we need to think about how we make enolates, okay, and enols, okay. I said that the process of enolization is acid catalyzed or base catalyzed. So you can use either catalytic acid or catalytic base to form the enol. If you use stoichiometric very strong base, you can make the enolate. We'll come to that too. We've actually shown that, but let's talk about just making the enol catalytically. So the base catalyzed process is not hard to understand at all. These protons are acidic. So in other words, if I have something like, let's take cyclohexanone, okay, just for the heck of it. Then I have protons here, and I'm going to just show protons on one side. You know, the ones on the other side are the same, you know that. And let's just take the ones here, the red ones. Now, it turns out the black protons are much more acidic than the red ones. So you know, with hydroxide, I never, ever have to worry about deprotonation here, deprotonation there, deprotonation there. If I treat this with hydroxide, the only place I'm going to pull protons off are from the alpha carbons. Now, why is that? Well, we kind of talked about that. If you look at the resonance structure for cyclohexanone, since we're talking about this, but it works for any ketone, the resonance structure looks like so. And so because of that positive charge, these protons here are much more acidic than they otherwise would be, and are removable by something like hydroxide. And so I can pull that proton off with hydroxide reversibly to get the enolate in low concentration. You're not going to, with hydroxide, you're not going to get 100% enolate, but then the hydroxide can get protonated either on the carbon, in which case it goes back, or it gets protonated on oxygen, in which case I end up with the enol. So loss of a proton, gain of a proton. Now, to repeat myself for the nth time, and I don't want to see this on an exam, what is the strongest acid present in aqueous base? Water. Very good. Okay. Don't show me H3O plus mix in there. So, pull a proton, form an enolate, add a proton, there's your enol. Simple. Doesn't get any simpler than that, right? So, how does it work with acid? Well, all of these reactions with acid, what's the first step? Proton transfer to the carbonyl. Okay, so you get a reversible protonation of the carbonyl. I mean, we've seen this umpteen times now. This happens reversibly, and it gives you this resonance stabilized cation. Okay, so now removal of the alpha proton by a very weak base, water. Now how does water do that? I mean, why does water pull this proton? I mean, how does that happen? Why? This is a cation. This isn't a resonance structure where you have a negative charge anywhere else. This is a cation. What do cations do? Remember what cations do? They form alkenes. This is something we've seen before. You have a cation that's just losing a proton to form an alkene, a reaction we've seen way back when and many times. And so you add a proton, you lose a proton, you end up with your enol. So again, this doesn't get much simpler. You just these reactions, these catalyzed reactions that go from ketone to enol, either with base, hydroxide, or acid, H3O plus, they take place the same way. It's just that the two steps are reversed here. Here you add the proton first, you add a proton, then lose one, whereas we did it the opposite sequence earlier. Now, there are some problems at the end of this chapter that ask you to think about this. One of the reactions, this turns out to have some utility sometimes. One of the reactions that takes place very easily is exchange of deuterium. So if I take a enolizable carbonyl compound and I treat it in excess D2O, heavy water, with a catalytic amount of acid or catalytic amount of base, then I will exchange rather quickly, because by the way, these equilibria establish themselves quickly. Rather quickly, these hydrogens will end up as deuteriums. That's because I'm using an large excess of D2O, so the Chatelier's principle is pushing this reaction that way. without giving away the problems that are at the end of the chapter, you should be able to see rather easily that if I take pentane-dione, like so, and I do the same thing, I use D2O, some big excess, and a catalytic amount of acid, that I will very quickly completely deuterate this molecule. So in other words, I will very quickly go to this. And the reason is because this is alpha-2-carbonyl, that's alpha-2-carbonyls actually, this is alpha-2-carbonyl. So all three positions are enolizable. If they can be enolized, then I can exchange the proton that was there for deuterium. So this may be one of the problems that you asked to do, I forget, but there are several similar ones at the end of the chapter. Okay, now the enol, and especially the enolate, the compound where I have a negative charge on oxygen, those are very good nucleophiles. And so I can do all kinds of nucleophilic substitution reactions via the enol or the enolate. And so let's take a look at a few of these. And the first one that we always talk about, seem to talk about, is halogenation. And so this is a reaction. Oh, and by the way, you saw that we can go from the ketone to the enol either under acid catalysis or base catalysis. And so what that kind of suggests to you, or should suggest to you, is that this chlorination reaction, or bromination, hydrogenation, whatever, this reaction is one that we can do with acid catalysis or base catalysis. Now, the two reactions, acid catalyzed halogenation, base catalyzed halogenation, are a little bit different, and you're going to see how. So let's try the acid catalyzed one first. And the acid catalyzed one, I've kind of given it away here. You take cyclohexanone, you take chlorine, and cyclohexanone is just, we could have picked any other enolizable ketone, I picked that one. Treat it with a catalytic amount of acid, and you end up with the monochlorocyclohexanone. Okay, now we need to understand why that is, right? Because you might have excess chlorine there. You expect maybe a little more than one chlorination. But actually, it stops after one. And so let's try to figure out why that is. So here's the mechanism. There's an acid. And so the first thing that happens, of course, is this reaction. You get proton transfer, acid-base. So here we go again with acid-base to give me, and I've summarized the steps, to give me the enol. Now the enol is what? It's a nucleophile, and it's a nucleophile on carbon. And so I can push the red arrows and show how I chlorinate that carbon atom. So this carbon atom, which had one hydrogen attached, there it is, now has a chlorine. I have a protonated carbonyl and chloride. Of course, this is an equilibrium with the product, NaHCl. And so this is an equilibrium with that. So you make the enol. Remember what I said about the enol. The enol, and especially the enolate, are carbon nucleophiles. It's a carbon nucleophile. It reacts with this electrophile. So not much different from what we've seen all along. Now, this reaction takes place in some steps, right? So the first step was enolization, and that was slow. Once you have the enol, then the enol is it's a reactive nucleophile, and so the reaction with the electrophile, chlorine in this case, takes place rapidly. What that tells you about the rate of this reaction is that the rate only depends on the concentration of ketone and concentration of acid, because these are the two concentrations that determine the rate of enolization. The concentration of chlorine doesn't enter the picture. Now, we've seen this before with SN1 reactions, right? Remember when we had SN1 reactions? We had the rate of the SN1 reaction, that's why it was 1, SN1, was unimolecular. It meant that the rate for an SN1 reaction was given by some rate constant K times the concentration of the alkyl halide. The nucleophile didn't enter the rate at all. And the first time you see that, I say, well, gosh, that doesn't make any sense at all. How's that even possible? remember we had, let's go back to SN1 and try to refresh our memories. So let's just take this solvolysis plus methanol. And remember that this gives you reversibly, a T-butyl cation, and that in the next step, you end up forming the methyl ether. And the byproduct I don't need to show here. Now the rate for this reaction, you will recall, was equal to some rate constant K times the concentration of T-butyl iodide. Why was that? Well, because the slow step, the rate determining step, was the formation of the cation. And the second step was fast. So the first step is slow, second step fast. And that's why the concentration of methanol here, or whatever nucleophile you have, doesn't really matter. Okay, so it's the same thing with the enolization. The first step is slow, second step is fast, and so the rate doesn't depend on the chlorine concentration. The chlorine never gets into the act until after the rate limiting step. So in the rate limiting transition state, chlorine isn't there. If it's not there in the rate limiting transition state, guess what? It's not there in the rate expression either. And so the rate for the chlorination under acid catalyzed conditions depends only on concentration of ketone and acid. Okay, so I've kind of spelled that out here. Now, the next thing we need to figure out is how come, because I can write a really good mechanism for second chlorination. I mean, the mechanism that you see on the screen there doesn't violate any rules. I don't have octet rule violations. I haven't done anything super bad, but I have done something not good. So why don't I get a second chlorine? Okay, so protonation of that carbonyl can take place, and that carbonyl can then undergo enolization. So now I have an enol. So this is the same mechanism that you saw for acid catalyzed enolization. Add a proton, lose a proton, get the enol. Except the enol now has a chlorine. This chlorenol should be a nucleophile, should be able to add a second chlorine and get to here. But it doesn't. And why is that? Oh yeah? You know, no, it's not steric effects. I'm trying not to. I'm glad you're thinking. I'm glad to hear steric effects, but I have to caution everybody. That is usually the first explanation we reach for, and so be careful not to reach for steric effects as an explanation each and every time when there's something else maybe going on. No, it's not steric effects. As you'll see, that getting two chlorines on the same or two bromines on the same atom doesn't create a bad problem for us. Something else going on. Take a look at this cation here. What's wrong with that cation? It's got two electron withdrawing chlorines adjacent, right? So that cation is destabilized. It's destabilized by what? By the polar effect, by those two chlorines sucking electron density out of the carbon, so that you now have a cation and a partially positively charged carbon bonded together. No good. And so the transition state leading from here to this unstable cation is also high in energy, and so this doesn't happen. So the cation destabilized by the polar effect of two halogens, Hammond's postulate again, says that the transition state leading to that unstable cation is also not stable, therefore we don't see it. So bottom line, acid catalysis, one chlorine goes in. Second one doesn't go in. Why? Well, because the cation you have to generate is no good. It's unstable. Okay, so yeah, this is maybe a little bit different question. So how come we don't see the same kind of reactivity that we saw with alkenes? So when we let's not take cyclohexene, let's take cyclohexene. Keep this with chlorine, not radical conditions, okay, just ionic conditions. Then remember what happens. You get a chloronium ion. The chloronium ion gets attacked by chloride, and you end up with a trans dichloride. And so the question is, well, you know, what the heck, you know, we're supposed to see patterns in this stuff. So why is it that my pattern recognition here seems to be faulty? Because if I look at pattern recognition, then really the product I should get should be this, right? I mean, this is an alkene, because the trans-dichloride, this is an alkene, that's what I should get. And the answer is that I mean, there's nothing really wrong with that line of thinking. The problem is that that right there, that carbon atom is unstable. Okay, so why, if you were to get to there, what do you think would happen? So and this is, by the way, this is true for all, not just cyclohexanone. So let's just say that I had any old compound that's got this substructure. That's not a stable structure. Why is that? Well, because it reacts. Yeah, okay. So how does it react? Well, it reacts this way. You have a good leaving group, and this is very fast, spontaneous. And what this is that. It's the protonated carbonyl. You never get that. So bromide, chloride, whatever. Now you say, oh, but you know, we've seen cyanohydrins, haven't we? I mean, these are stable. Right? Cyanohydrins are stable. So what's the difference between this and that? Unstable, stable. Tell me. Yeah, chloride's a good leaving group. Cyanide is not. Chloride's a very weak base. Cyanide is a much stronger base. And so that's why this is stable and that's not. Okay? And so you know, I keep saying this, but I mean it. You guys need to always think about acid-base chemistry. A lot of what we do, most of what we do, kind of goes back to that, and that's how you can understand why that doesn't happen that way. So the bisphenol dichloride, which you would have gotten, is unstable, and it loses HCl to form the chloroketone, as I showed. Okay, so that was the acid catalyzed monochlorination of ketones. So now the question is, well, you know, I want to do this under base catalysis. What's going to happen? Well, let's take a look. So let's do something just a tiny bit different here. We could have done this with cyclohexanone, but it's more interesting to do it with a methyl ketone because of what happens next. And this is called pinacolone, actually, and why is this called pinacolone? Because of a rearrangement that you have seen, actually, and the rearrangement is this. I have this diol, okay? That diol is called pinacol. Don't ask me why. And if I treat this with acid, somebody tell me, what's the first step? The first step is going to be acid-base reaction. I'm not going to push arrows for you here. You can figure it out. Okay? And so there's acid-base reaction. That takes place reversibly, right? Now, the next step is an interesting one. It involves migration. It involves a methyl migration. There's the methyl group that migrates, this one right here, with its electron pair, and expulsion of water. That's a cationic rearrangement. This is irreversible. What does that give us? Well, let's draw out everything that didn't change. And now the migrating methyl group is here. There it is. So you got a 1,2 methyl migration. This is a problem that you saw in Chem 272, I'm pretty sure, when we talked about cationic rearrangements. Okay, so that's pinacolone. That's this ketone. That's how they make it. Now, take pinacolone. Notice that one side is a T-butyl group, the other side is a methyl on the carbonyl. So the carbonyl is flanked by a T-butyl. The T-butyl, by the way, does not have any hydrogen, so it can't enolize on the left-hand side. Why can't it enolize? Well, because there's no hydrogen to lose. So this can only form an enol on the right-hand side because that's where the hydrogens are. So if you treat this with 3 equivalents of bromine hydroxide and do it at low temperature, you end up with this tribromal ketone. And so notice the difference. If you do this with acid, 1 halogen. You do it with base, all enolizable protons get exchanged, each and every one of them. So if I did the same reaction, not with pentacolone, but with cyclohexanone, the same reaction that we did before, how many enolizable protons do I have in cyclohexanone? Well, count them up. I've got 4. So if I treat this with base and bromine, then what I'm going to end up with is, you know exactly what, I'm going to end up with a tetrabromo cyclohexanone. And so all enolizable protons here are going to be exchanged with bromines in base, not acid in base. Now, the fact that you get a different kind of product in acid from what you get in base tells you what? It tells you that the mechanisms have to be completely different, and they are. Well, of course they are. In one case you got base, in one case acid. I mean, of course we're different. So, but the first step is pretty much the same. So the first step involves enolization of the pentacolone. And so you end up with hydroxide forming either the enolate or the enol, makes no difference. And this gets brominated. Okay? So you get proton loss reversibly. The enolate gets brominated. But now look at the acidity of the proton. This proton, compared to the one here, this one's more acidic. Why is that? So once you add the first bromine, the protons that are left attached to the alpha carbon atom are more acidic in the product than they were in the starting material. Why? Well, for the same reason, because the bromine is electron withdrawing, and so the enolate that you form, which enolate? This enolate is stabilized relative to that one. Why is this enolate stabilized? Well, because the bromine is electron withdrawing, and this is negatively charged, which means that you start with a slow step, and then this is faster and faster, and so it goes. So each successive bromination is faster than the preceding one, and so the polar effect of that bromine acidifies these protons, and so the second enolization is faster. You get a second bromination. Once you have the second bromination, the proton that's left, that last one, is even more acidic, so that one's lost even faster, and so it goes all the way to the tribromal compound. Okay? Now, so it kind of makes sense on the basis, and I haven't shown the third bromination, it's just the same, it's the same as the first two. So it kind of makes sense based on what? Well, based on acid-base chemistry that we know about. Okay, so that's good. Now, what happens next is kind of interesting, because this is really quite unexpected. There's a test that we used to do in the organic chemistry lab to test for the presence of a methyl ketone. So if you have any kind of organic molecule that's got an R group here, and R is alkyl, phenyl, whatever, and has a methyl group, then there's a diagnostic test that you can do that tells you that it is a methyl ketone. Now you can say that, why on earth do I need a diagnostic test like that? Because, hey, I'm smart, I know about proton NMR, and I know that I can look for that methyl group at around 2 point something ppm. And if I have a carbonyl group that's around 1720 or 1710 in the IR, that nails it. And so the answer to your question is, yeah, you're all correct, you're right, and that's how you do it in the year 2016. But a lot of these diagnostic tests were developed at a time before spectroscopy was available. And so it turns out that if you take bromine and base, and you take this ketone, one of the compounds you get is this, which goes by the trivial name of bromoform. Now, if you heard of chloroform, chloroform is just Cl3CH. Bromoform is this stuff. And so if you have iodo, it's iodoform. So this is known as the haloform reaction. Now, how this works is really weird. Look. Remember the product that we got from pentacolone and bromine? Here it is. Now, you may not have noticed the bromination was done at 0. Okay, that was for a reason. So if I heat this up a little bit, in the presence of hydroxide, and this is what happens. Hydroxide is a nucleophile. It's a base, but there's no proton for it to pull off. So now it can act as a nucleophile. It forms this tetrahedral intermediate. When this tetrahedral intermediate collapses, according to what I've shown with the red arrows, look at what you get. You get a carboxylic acid, and you get CBr3 minus. Now, the first time you see that, you say, boy, this looks really screwy. Why? Is this a leaving group? I mean, usually it's a carbanion, for Pete's sake. And so carbanions typically are extremely strong bases. They are not leaving groups under any sense. Why would this one be different? Why would that particular carbanion be able to function as a leaving group? I mean, normally you don't see that, right? In fact, I told you on whenever it was, on Monday, that when you do a nucleophilic addition to a ketone, or to an ester or whatever, you don't spit out from the tetrahedral intermediate, you don't spit out a carbanion, because I said the carbanion is a very strong base, and it is not a leaving group. So how come this one's a leaving group? What does that tell you? Yeah, it can't be a strong base. And the reason it's not a strong base is because the three bromines are pulling the electron density, are stabilizing the electron density here. So this is actually able to function as a leaving group. And of course, once this happens, you get an irreversible proton transfer, and you end up with the carboxylate. Now this is really, really weird. But it is one of the few cases where you're going to see a carbanion as a leaving group. So stabilized by 3 electron withdrawing bromine atoms, and I mean it's not a good leaving group, but I mean as long as you get even a little bit of this, you know, Le principle pushes it all the way. When I say it's a good leaving group, I mean compared to methyl lithium, for example, it's still a strong base, but not nearly as strong as methyl lithium. What the pKa of this stuff is, I'm not exactly sure, but it's probably at least 20 orders of magnitude less than say methyl lithium. So it's a huge, huge difference. Okay, so that was bromination, chlorination of ketones, but acids, carboxylic acids, can also undergo similar reactions, right? Because carboxylic acids, esters, amines, lactones, lactams, anything that can form an enol can react pretty much the same way as a ketone enol, right? So an enol is an enol. I mean, they have different reactivities, but the paradigm is going to be the same. Now, one of the nice things you'll notice is that a lot of these reactions bear the names of the discoverers, and you don't need to remember this one, but Harold Zielinski reaction. These are chemists who worked on this at the turn of the 19th century, if memory serves. So you take the carboxylic acid, in this case hexanoic acid, bromine, and it turns out you need a catalytic amount of PBr3, okay, or phosphorus. You can use elemental phosphorus because the elemental phosphorus with bromine gets converted to PBr3. So the PBr3 is the true catalyst. This reaction is catalyzed by PBr3. And what you end up getting is the alpha bromo acid in very good yield, by the way. So if you leave the phosphorus out, nothing much happens. So phosphorus is doing something for us, right? This is kind of puzzling. Elemental phosphorus is not something you usually want to work with. It's pretty hazardous, and it's been used by many countries, including the United States, as a weapon of war. And so you're better off catalyzing this with PBr3. So what's going on? I mean, I'm not asking for details. The PBr3 must be doing what to become? It must be enabling some process. What process do you suppose is being enabled by the PBr3? bromination now, but before bromination. How do we get the bromination of the ketone? What had to happen first? Yeah, it had to enolize it. So the phosphorus tribromide is somehow helping us enolize the carboxylic acid. So now what you think of is, gee, how come I need help? Because I didn't need to use phosphorus with with ketones. In fact, all I had to do was treat it with bromine, a little bit of acid, and it enolized, or chlorine and acid, or whatever. And here you need a catalyst. What's the key difference between the enol of a carboxylic acid and the enol of, say, cyclohexanone? There's a difference, big difference. What is it? Well, one's got an extra oxygen, okay, but that's not what I'm asking. Why would you need to catalyze it? Well, what do catalysts do? Yeah, they lower the activation energy and make it go faster, which means that in the absence of the catalyst, enolization of carboxylic acid is slow as molasses, right? Slow, slow, slow. Why? Why would it be slow? Yeah, because the enol is not, for the carboxylic acid, has a higher activation, you have a higher activation energy to overcome than for the ketone. And the reason for that is the reactivity series. Remember that the carboxylic acids and esters are more stable, less reactive than ketones. And so enolizing them harder. So somehow that PBr3 is helping us enolize the acid. Now, if you remember the reactivity series, it turns out that the acid bromide is the least stable, right? Acid chlorides, those are the most reactive. And so you have a stable carbonyl group in the carboxylic acid, but with PBr3 you form the acid bromide. Now you've converted stable to unstable carbonyl. This one can enolize. And so this carbonyl group can enolize at least a little bit, so you have an equilibrium here, and that can undergo bromination. And so it's kind of a clever trick, right? Because you go from carboxylic acid to anhydride to aldehyde to ketone to carboxylic acid. You add the PBr3, you leapfrog all the way to the high end of the reactivity scale, which is the acid bromide, which can enolize, and it does. And because it enolizes, it undergoes bromination. So now you look at this, say, well, okay, fine, maybe I believe this, maybe I don't, but if that's the case, then how come I isolated the alpha bromo carboxylic acid? How come I didn't isolate the alpha bromo acid bromide? And here's where the catalytic cycle gets to be interesting, because what happens is this. You do get this, obviously. And if you use a full equivalent of PBr3, that's where it goes. But if you use catalytic PBr3 or catalytic phosphorus, then you get an exchange reaction. This stuff and that stuff come together to give you the product in the acid bromide. This then undergoes enolization bromination, and this enters the catalytic cycle again. And so it's a very clever way of catalyzing this reaction. The acid bromide does an exchange with the free carboxylic acid, and so you end up getting this equilibrium, and then this can enolize again, and so on. So then the question is, well, how come this doesn't enolize again? And why is that? Why does this enolize a second time? I need to think about that. Oh, well, because acid catalyzed, same thing as before. Okay, so let's go over this one more time. Hopeful Zelinsky. So you don't have to use PBr3. You can use elemental phosphorus. These will react to your PBr3. The PBr3 is your catalyst. So what the PBr3 does the same thing to a carboxylic acid as it did with an alcohol. Remember that we talked about how you take a primary or secondary alkyl and convert it to the alkyl bromide? One way is with PBr3. Well, this is pretty much the same mechanism. I'm not showing the mechanism here, but you guys can figure it out based on what you saw for alcohols. You get the acid bromide. This doesn't enolize, that does. So this forms the enol. The enol undergoes bromination. Now you get a little bit of this. But this reacts with starting material. And so it reacts with starting material in an exchange. Bromine ends up here, hydroxide ends up there. So there's your product, and there's your acid bromide. This is the same acid bromide that we had up here. And so the catalytic cycle continues. And so this is how you get alpha bromo carboxylic acids. These alpha bromo carboxylic acids are useful for various things, and they are common articles of commerce. So you can buy these things pretty cheaply. They're made this way. This is how they're made. Okay, now, why take an interest in alpha halocarbonyl compounds? And the answer to that is because they're reactive. You can use them just the way we did with alkyl halides. Remember, we used alkyl halides as starting materials for a bunch of other kinds of products. You can do the same thing with an alpha halocarbonyl. So if I compare these two structures, this is a reactive allylic bromide. This looks pretty much the same, right? I mean, it looks like an allylic bromide. And so the reactivity is similar to an allylic bromide. You might be interested to know that, I don't know if this is, okay, well, I know the property. This, I don't think it's the one they use, but this stuff here, alpha chloracetone, is a pretty good lacrimator, which means it makes it a tear gas. It makes your eyes tear up. Why would that be? I mean, acetone, you ladies use that to remove fingernail polish. You don't tear up every time you take off the fingernail polish. So acetone itself doesn't do anything like that, but chloracetone and much more bromoacetone, you'll feel that if there's a little bit of that stuff in the air, you'll know it right away. Why is that? I think the commercial, yeah, just remember, I think the commercial tear gas, and the one that you know, if you're riding, they spray at you is this stuff here, one of them. So why are these things, why is alpha chloracetone lacrimator? Yeah, exactly right. So it's reactive. It's like an allylic halide, and so you end up with HCl. And so it's a strong irritant for your eyes. So see, the police are able to pour acid into your eyes with impunity. Okay, so usually when we have acid alkyl halides, bromides, chlorides, whatever, we do SN2 chemistry, SN1 chemistry, stuff like that. You do displacement with the nucleophile. Now, with alpha bromo ketones, alpha bromoaldehydes, alpha chloroketones, alpha chloraldehydes, yes, you can do nucleophilic displacement chemistry, but you have to be careful. Here's why. So let's just take an alpha bromoaldehyde, okay? And I'm going to give it away a little bit. So there's the alpha bromoaldehyde. Here's the bromide. It's a secondary allylic bromide. I should be able to do nice displacement chemistry on that. However, if my nucleophile is strongly basic, then bad things are likely to happen. I should say bad things. Something else will happen. You won't get the displacement. What will happen is that you'll have a competition with proton transfer to that to the basic nucleophile. This proton is basic. is acidic, pardon me. And it's acidic because it's acidified not only by being next to a carbonyl, but also by this bromine. So for the same reason that we saw complete bromination and formation of CBr3- in the bromoform reaction, same thing here. If you try to do displacement of that bromide with anything that's basic, you'll end up forming the enolate. Now recall that the enolate, once formed, will look like this. So this will be your aldehyde enolate. If you form that enolate, you no longer have an sp3 hybridized carbon atom. This vinyl bromide is inert to nucleophiles. And so we'll pick up that discussion on Friday.